Hello and welcome to the third episode of the Space from Home podcast. My name is Daniel Verscharen and I'm a lecturer in space plasma physics at the University College London's Mullard Space Science Laboratory. In this podcast, I tell you a little bit about the work of space scientists and engineers during the time of the COVID-19 situation. I spent quite a lot of time this last week calculating dispersion relations. So I thought it would be good to discuss with you what a dispersion relation actually is, why it is important, and what we can do with that. Dispersion relations are definitely something that space physicists work a lot with, and something that we can do more or less easily from home in these days. In principle, dispersion relations have to do with waves, like sound waves in the air or water waves in the ocean. In this case, I'm interested in waves in the solar wind. A quick reminder, the solar wind is the very thin gas of charged particles that fills the space between the planets. It flows away from the Sun with a speed of about 500 kilometers per second, and it has a temperature of a few 100,000 degrees, although these numbers can vary a lot over time. The solar wind is an example of a plasma, which means that the negatively charged electrons are separated from the positively charged atom nuclei that you would also find in a normal gas, like in the air. Because we have these free charges, the plasma, the solar wind, reacts in somewhat strange ways to electric and magnetic fields. Because of these strange interactions between the charged particles in the plasma and the fields, there are very many different types of waves that can propagate in this very thin plasma. Some of these waves are similar to those that we know here on Earth, like sound waves, for example, but others are very unusual. The really great thing about waves in the solar wind is that we can actually measure them with spacecraft, like with our Solar Orbiter spacecraft. I want to show you a couple of measurements from different spacecraft today. Here you see a really great NASA spacecraft called WIND. WIND launched in 1994, and after some other mission objectives at the beginning, it's been measuring the solar wind right in front of the Earth continuously for the last 16 years. As you can imagine, such a huge data set of solar wind measurements is really useful for our science. On this picture, you see an example of measurements from the WIND spacecraft. This is just a time interval of 7 hours in the solar wind. The wiggly blue lines give you the changes of the solar wind speed during this time, and the wiggly red lines give you the changes of the magnetic field at the same location and during the same time interval. These wiggles that you see in this picture are actually one type of these plasma waves that I've been talking about. As you see, the solar wind is not just a super smooth flow of gas, but there are a lot of variations in there. When we look at these waves in some more detail, we see that they are a very special type of wave called an Alfvén wave. It is named after the Swedish plasma physicist Hannes Alfvén, who also received a Nobel Prize for his development of the mathematics that lies behind this type of waves, and also behind many other phenomena in space plasma. There are a lot of other types of waves in the solar wind. Here is a really nice movie made by NASA that illustrates some types of these waves. The little arrows show the direction of the electric and magnetic fields in these waves. As you can see, sometimes they rotate in different directions, and sometimes the arrows only change their length, but in either case, they always propagate through the material with changes in the fields. Of course, this looks very smooth in this animation, and reality is a bit more complicated, but in principle, this is what these waves do. You can nicely see how the waves propagate to the right-hand side in this animation. Now the question is, why do we care about these waves so much? Well, as I said, they come with changes in the electric and magnetic fields in the solar wind. The really interesting thing about electric and magnetic fields is that they can change what the particles are doing, so what the actual solar wind is doing. For example, an electric field can give energy to the particles, it can make them faster, or it can even make them hotter, depending on how this interaction works. The acceleration and heating of particles are two very important and fundamental science questions in the field of space physics. Here is another really nice movie from NASA. It shows two little particles in the solar wind, for example, two electrons. At the start, they only circulate around the magnetic field like all charged particles would do. But now we add a wave to this. And you see, depending on how fast the wave and the particle are, the particles can begin to interact with this wave. And in this case, the particle at the top has gained energy. So, if we want to understand what the energy does in the solar wind, then we have to understand how these interactions between waves and particles work. Now, the dispersion relation is actually a mathematical way to describe how these waves work. There is a very powerful mathematical theory that allows us to calculate how fast these waves propagate, how fast these waves give their energy to the particles, and many other properties of these waves. For example, we can find out how the electric and magnetic fields rotate, and we can even calculate how the density of the plasma fluctuates in these waves, which it sometimes does, as we know from satellite observations. Because the equations of this theory are a bit complicated to be solved on paper, we have some nice computer programs that help us to calculate the answer. For example, I've written the NHDS code, which you can even download and play with for free if you are interested. In principle, we just have to put in the right parameters of the solar wind, for example, its density, its temperature, or how the different ions and the electrons move on average, and then the code gives us a series of numbers that tell us what the plasma waves are doing. These numbers look really weird for someone who isn't familiar with this, but for a space physicist, this is very valuable information. Here you see an example of a dispersion relation in a diagram. In this case, I've been trying to understand a type of wave in the solar wind near the Earth that was observed by NASA's MMS mission, a mission that consists of 4 spacecraft. I used the solar wind conditions that MMS measured and then calculated how some really small Alfvén waves would behave there. This diagram tells us how these waves move, how they exchange energy, and how other properties vary depending on the size of the wave. We can then go back to the measurements and check, do we actually see a wave that looks like this? And if so, then we now have a confirmation from plasma wave theory that this type of wave is actually present, and we can then investigate their properties further. I can already tell you that in this time interval, we actually found those waves, so we're now preparing a scientific publication about this finding. Many different types of plasma waves also exist much closer to Earth, within the so-called magnetosphere. The magnetosphere is the environment around the Earth that forms by the interaction of the solar wind with the Earth's magnetic field and with the particles that, for example, come from the Earth's atmosphere. As shown in this nice artist impression, there are also many plasma waves in the magnetosphere and in other environments around the Earth. Since the conditions here are a bit different from the conditions outside in the open solar wind, we have to calculate these waves and their dispersion relations separately. I also did some of these calculations in the last week to compare with measurements from other satellites, and again, the dispersion relation helps us to understand the waves that we observe and to understand what these waves actually do with the plasma. Dispersion relations can do even more. They can also help us to understand instabilities in the plasma. In instabilities, some mechanism drives waves so that they grow and grow in their amplitude over time. In water waves, like in our ocean, for example, the wind can drive waves and make their amplitudes grow and grow over time. In the solar wind or in the magnetosphere, there are other processes that can do this, but maybe we should speak about instabilities at another time. I hope I could show you that dispersion relations are really useful to interpret and to understand spacecraft measurements. They give us a great insight into what waves are doing and how energy moves around in a plasma like in the solar wind, which is a big open science question in space physics. If you like this short look into space from home, then please like and share this video, and hopefully I'll see you around next time. Until then, take care and stay safe. Goodbye.